Okay, so now I just want to sort of close the discussion for this week by connecting the ideas of maximum likelihood estimate that you learned before with the d-squared estimate that we've done so far. So for this, we have to assume something about the errors. So I will call this assumptions of normality. Assumption of normality. So here what I'll do is, until now, I already assumed that either the random variable y or the errors, how you want to look at it, are uncorrelated, and the errors have variance sigma square. But now, in our linear model, I'll assume I'll assume y is normal. Okay, y is normal with mean x beta and variance sigma squared I in cos. Okay. So it's a little bit more than just uncorrelated. So why I'm going to assume y has a distribution as normal and variance sigma squared I n. So with mean x beta and variance sigma squared I n. So that's what I'm going to assume. So that is, so just to sort of recap, that is before we had the linear models y, x beta, and sigma squared I n cross n. That linear model has an extra assumption that the error terms are normally distributed. Has an extra assumption that the errors are normal. That the errors are normal. That the errors E are normal with mean 0 and variance sigma squared I n cross n. That's what it is. Very good. So now, see, given if I give you this normal with parameter, mean parameter x beta and variance sigma squared I can always write a likelihood function given one. Right? So recall, so the likelihood function for, let's say, I'll just call it the two parameters of what beta and sigma squared, this is what we don't know, right? Or beta and sigma squared is given by what now? Since the distribution is normal, I can write down likelihood. I can say the likelihood of beta sigma squared given my vector y, right? What's that going to be? That's going to be equal to, now it says normal density, right? It's multivariate normal density. So it's 1 over, let me move the clock a little bit here. So it's 1 over 2 pi to the n by 2, right? I have sigma to the power n. I have exponent of, I have minus 1 by 2 sigma squared, because it's still uncorrelated. I'll have y minus x beta, that's the mean, transpose times y minus x beta. And that's what the density looks like. Right? That if you just do a little bit more carefully, that's the same as 1 over 2 pi n by 2 sigma n, sigma power n. And here I'll write as exponent of minus 1 by 2 sigma squared of norm of y minus x beta, the whole square. Right. So all these are vectors, I'll put lines there. So now it should ring a bell immediately, right? Because now you want to maximize the likelihood for beta and sigma squared, right? That's the same as minimizing y minus beta. So suppose sigma squared was known, maximizing likelihood beta is same as minimizing y minus x beta squared. because of the negative sign here and exponent being increasing function. Therefore, the MLE for beta and sigma squared is same as the least squared estimate for this guy. So therefore, thus, if sigma positive is given, right, I go and maximize over all possible beta in Rm of the likelihood function beta sigma squared given y. That's the same as minimizing norm y minus x beta squared where beta is an Rm. Okay. But now we know, right? This guy here is the MLE of beta, the maximum likelihood estimate of beta. Okay. And this person here, we know is the least squared estimate of beta. So the two things will match. That is, the MLE problem and the least square estimate problem match under the assumption of normality. That's one. The MLE is the same as the least squared, but once you have normal, because the likelihood functions are match nicely. Okay. So some remarks, and I'll close with this. This is one motivation for doing least squares. So typically, when you do least squares in the beginning, you just say, okay, I minimize y minus x beta. I have these points. I want to find the best fit line, and that's how I start this whole idea, right? But the motivation of starting the best fit line is that under normality, it is the MLE is the least square estimate for beta. That's the word. So now let's do some remarks, and I'll close for the day, for the week. Here's some remarks. The first is that the MLE of beta exists, but may not be unique, right? So first thing I understand. So MLE may exist. MLE of beta may exist. The calculus, but may not be unique. First thing you understand, right? The second thing is it's unique. When is it unique? It's unique when the right-hand side problem is solvable, right? So that's when you know it's unique. But you know right-hand side problem has a unique solution if the rank of x is m. That's what we did today. Okay? So that means, so the MLE is unique. It's unique if and only if the rank of x is m. That's what we did today. What's the next one we can do from this whole calculation? So you look at the likelihood function. You look at P transpose beta. You know it's estimable. Then the MLE of P transpose beta is unique. It's given by the least square estimate. And P transpose hat beta hat is the least square solution, is a normal sort of a normal equation. Write that down. So if P transpose beta is estimable, right? Then the MLE of P transpose beta is unique, because we know that that's how you've shown that today is unique, given by its least squared estimate, that is, I write this down, that is P transpose beta hat is the solution, P transpose beta hat for any solution of the normal equation, that is normal equations. Equation x transpose x beta hat is x transpose y. That's one remark. Then from this, again, this MLE idea, we can go again, I can go back and say eta equal to x beta, right? Has the unique, how do you know has unique MLE? Has a unique MLE. You can either go normal equations, or we can go, you can say eta hat is x beta hat, and x beta hat is just the orthogonal projection on the column space of x times y vector. So that's the MLE for x beta. Right. The other thing you can also observe is that this eta hat is going to be normal, right? It's going to be normal with mean x beta, right? And variance sigma squared px. That's what we computed today. The blue is sigma squared. So the MLE will have all these things probably.